Okay, so today, new topic. Nope, not that topic. How about this one? We're going to talk about the discrete Fourier transform. Now, you probably feel like you've already talked about discrete Fourier transforms, but you haven't. We've talked about the discrete time Fourier transform, the DTFT. This is the DFT. Also sometimes called the FFT, the fast Fourier transform. Actually, a fast Fourier transform is just a clever way to compute the discrete Fourier transform that's really good for computers. But it's also this discrete Fourier transform and the fast algorithm for computing it that we call the FFT is what makes signal processing on the computer possible. And so it's a very worthwhile topic, something good to know about. And to understand it, and we'll do today is try to relate it to stuff we know, the DTFT, see how it's the same, see how it's different, and talk about a little bit about some of the subtleties of what makes a difference and how that affects the way we use it when we do some of the common things that we would want to do with transforms, like doing convolutions with the frequency domain, or looking at the spectrums of signals. To understand some of the quirks of the DFT, it's easiest to start with a place that we know, the Fourier series for a continuous time signal, right? Monsieur Fourier came along and said, you give me continuous periodic time function, I give you spectrum. And that spectrum will have some very particular characteristics. It will have individual values whose spacing is very particular. These are harmonic frequency samples that happen in integer multiples of the fundamental frequency of my original periodic signal. And so, okay, well, that's cool by itself. For today's purposes, what we want to notice is, periodic thing over here gives me discrete thing over here. Okay? If I have a periodically repeating time function, its spectrum only has discrete values. It doesn't have values in between these. It only has certain frequency components. Okay. Well, we flipped that on edge when we started down the path of discrete time signals. Now we have sampled data signals. We have samples in the time domain. And we saw already that the result of that, the implication of that, was when we created a spectrum using the Fourier transform. That spectrum was repeating now. Right? It is periodically repeating continuous spectrum, the DTFT, which we could look at either in what we call the principal range from f equals -1/2 to +1/2, and everything else is just periodically repeating copies of that. If it was a real function in time, we have certain symmetries. We're even symmetric for magnitude around the f equals 0 and f equals 1/2 Nyquist, and also all the integer multiples of those. But we saw the dual of that original Fourier series connection. That periodic here gave me sampled here, here sampled here gave me periodic over here, in traded places. But there was this connection between if I have periodicity in one domain, I have sampled in the other, or vice versa. If I have sampled values in one domain, I get periodic in the other. Well, the DTFT, we also know the definition of that. We've already studied that. It's a summation over all the sample values of our time function multiplied by e to the minus j2 pi n capital F, where F is a continuous variable, not a discrete variable, a continuous one. So the discrete time Fourier transform spectrum is a continuous spectrum, but it's periodically repeating. The DFT is a little different. If your time function that you take the discrete Fourier transform of is a finite length sequence and has m samples, so maybe it's indexed and goes from 0 to n-1. If I take the DFT of that m samples, what I get is another finite length discrete sequence that has the same length. If I put 5 samples in, compute 5, I'll get 5 frequency sample values. it looks similar. It's a summation over all the non-zeros, some finite number of h of n sample values, times e to the minus j 2 pi n. Instead of f, I have k over m, where m is the number of samples that I have in here. So my sum goes from 0 to n minus 1. And k is an integer index for my frequency, my discrete time Fourier, my discrete Fourier transform sample values, the frequency samples. So this ratio, k is an integer, n is an integer, ratio of 2 integers. So the way we interpret this, when we did with this DFT, we said, okay, I'll do this summation, and hopefully I'll get a closed form sum. I can have some analytical function that's a continuous function of frequency. This one, yeah, I just want sample values. And for each sample value, I plug in the k value I want, put it in for here, do the summation, and I get a sample. Put in the next value of k, put it in this formulation, get another sample, one at a time. That's tedious for us. Computers love it. That's why the DFT is so powerful, because it's a simple summation that's just chunking through a bunch of numbers, and computers are good at that. And giving discrete answers, not continuous functions. Right? So if we compare the two, again, the differences are the DTFT is a continuous spectrum, a continuous frequency variable f takes on all values. This only has certain sample values for k equals 0, k equals 1, up to n minus 1. Otherwise, they look the same, except we assume this is a finite length sequence. And my frequency variable now is this ratio k over m. So this thing, the DFT, the discrete Fourier transform, is again periodic. The repeating spectrum, it has to be because I'm starting with time samples. I get a finite number of answers, a finite number of sample values. So it turns out those m samples are one period of the periodically repeating spectrum. So let's say you have a frequency spectrum of a low-pass signal, or maybe a low-pass filter's frequency response. It's discrete time Fourier transform, you can end up doing something like this, up to the Nyquist frequency, and we know due to the symmetries, at negative frequencies, it's a mirror image of that. Above the Nyquist frequency, it's also a mirror image, and we have this repeating spectrum. Okay? We keep plugging in higher and higher values of f in the discrete time Fourier transform, keep tracing this out on and on and on. What do we get out of the DFT, discrete Fourier transform? Well, you give me m samples, maybe 11. What I'm going to do is break up this range of frequencies from f equals 0 to f equals 1 into the same number of samples. So if I have 11 samples in a time domain signal that I transform, I get 11 frequency samples. And those happen at, well, indices k equals 0, 1, 2, 3, 4, 5, 6, 7, up to 10. What frequency they occur at is, well, k over m. If m is 11, I get 1 at 0, 1 at 1 over 11, 2 over 11, 3 11. So I'm breaking up a range of 0 to 1 into m samples. So I have 1 over m spacing between them. So the number of samples reciprocal of that tells me how widely spaced are each of these samples in frequency. You see how we do that? So we take 0 to 1, break it up into m samples, and that's the answers I get out of the DFT. On a good day, I get samples of the continuous DTFT spectrum over the range of frequencies from 0 to almost 1. So my resolution, how close I get to the spacing between them is 1 over m. Notice I don't get a sample value at f equals 1 because I already got it. It's here. And I can pick up these m samples and just keep making copies, making copies, making copies. So that's what I get out of the DFT. Now, notice this transform requires me to rethink the way I look at spectra. I spent an awful lot of time telling you the principal range goes from frequency -1/2 to +1/2, right? Yet when I use a DFT, that's not the range I get 0 to 1. But that's okay. I still have all the information I need. These samples over here, the negative frequency side, are these guys. Just picked up and moved over here. So all the information's there, all the data's there. I just have to be careful how I think about it. Right? Kind of like we were doing when we were talking about frequency responses. You know, we have to reorient our thinking. High frequency is not all the way over here. High frequency now is, well, Nyquist is as high as I can go. So here's high frequency. This stuff is not high frequency. This is the negative frequency stuff. We'll just take a little visual reorienting when we're using the DFT. So remember, these upper values, these later samples represent, well, they do represent these high frequencies, these higher above the Nyquist frequencies, but they also are the ones for the negative side. That's periodic. Okay. So on a good day, discrete Fourier transform is a sampled version of the DTFT. It's going to take us the rest of the next half hour to explain what a good day is and what a good day isn't, because it doesn't always work out quite so nicely. Before we go on to that, questions are okay with how they're related so far? Okay. How do you compute them? Well, you literally just work through this summation, plug in k equals 1, go through the summation. Plug in k equals 2, and so on and so on. If you keep k as a variable and work out the summation, well, it's summation over n, from n equals 0 to n minus 1, so we get h of 0, h of 1, h of 2, and keep increasing n in the exponential. And for each sample value I want, just plug in a different value of k. So for example, for the h of 0 term, you plug in k equals 0 up here, we get h of 0 plus h of 1 even minus h of pi k 0. This one, we have k, we have zeros. And lo and behold, the h of 0 term, all these exponentials are e to the j zeros, and we get that the h of 0 term, the DC term, if you will, in the discrete Fourier transform is not the average value, but the sum. And that's actually the same result we derived from the discrete time Fourier transform. So that much the same. If I wanted to know what's h of 2, well, and I plug in k, or plug in k equals 2 here, k equals 2 there, and compute the summation. Okay. To be useful, we need an inverse transform. Well, so again, we'll use our nomenclature, capital letters for the transform, little letters for time domain. We have a discrete transform values now, h of k, for k equals 0 to n minus 1. If that's the DFT of h of n, finite length sequence, if I have m samples in here, I have m frequency samples. I take the inverse transform of this m samples, I should get a time function that I would love to be the same as h of n, where I started. So we'd like this to be a reversible transform. The h of n, transform it, inverse transform it, get the same thing back. I'm not ready to say they're the same yet. I'm going to put a little prime there. That's not a derivative. That's a, this h of n may not be exactly the same as that. If I perform the DTFT and an inverse DTFT, h of n will be the same here and here. When I do the discrete version, though, I can mess things up. I can get something back that wasn't what I sent in. How we would compute it, here's the inverse transform formulation. As with all inverse transform, it's still the function now, a discrete function, discrete frequency values, not continuous. So I think that the inverse DFT inverse DTFT with an interval. This is a summation of our frequency sample values multiplied by e to the plus j2 pi n here. So the exponential argument is the same except it's positive instead of negative. And the other difference, you get a 1 over n. Where m is again the number of samples. Okay. Whew. So you have Fourier transform, inverse transform. I'm saying they're about the same thing as the DTFT, but not always, kind of, sort of. I'm using very cryptic language here. Let's dig into this, see what's going on here. When do we use this? Well, everywhere we would do anything in the frequency domain, we're going to do it with a DFT, especially if we have a computer laying around. We all have computers in our back pockets now. And so, if you want to look at, plot, or estimate the frequency spectrum of a signal, we're going to use a DFT. You've all used the sampling oscilloscopes in the 368 lab and other labs. Do the math function, hit FFT, and it shows you a frequency spectrum of a signal. Right? It's using this computation to compute those values. It's sampling that signal coming in from the probe, running it through a DFT, well actually an FFT, the fast version, and showing you the magnitude samples on the screen. So we would definitely use this for discrete signals. We also used it for looking at the spectrum of continuous signals by sampling them first and then running them through the DFT. Another big use would be for doing fast convolution. Now, up until now, we've talked about using Z transforms and DTFTs as an alternate way to do convolution, because for us it was mechanically simpler to come up with analytical functions, analytical results, if we did transforms, frequency domain multiplication, and inverse transforms, instead of doing the trudging through the sample values for convolution. Well, it turns out that process is easier and faster and more efficient on computers to do it with these transforms than doing the actual convolution computations. Because if I convolve two sequences, if they're both the same length, like plate M, I need M squared computations. If I do them with these transforms, well, if I just did pure DFT transforms and multiplication and inverse transforms, I would probably end up doing more work. But because I can do these DFTs with a very clever, very efficient algorithm called the FFT, it's actually computationally much more efficient for a computer to do it this way than this way. It saves a lot of computations. And so it makes digital signal processing fast and efficient. So if I want to do convolution, I'll do it in the frequency domain with inverse and forward DFT transforms. So, question of the day, one of the questions of the day is, all right, I take my samples, I take some discrete time signal, take the samples, take the DFT, I get, boom, transform, spectrum, samples. Is this the correct, the true, the real spectrum for my original signal? What do you think? No. Good guess. No. The answer is no. The real, the true, the correct spectrum for that discrete time signal is the DTFT, the thing with the continuous function at all frequencies, periodically repeating, and that is the correct spectrum. That the mathematicians would be happiest with that. So if the DFT is not the correct spectrum, why do I use it? Why do I like it? Well, at best, it gives me a discrete version, a sampled version of that correct spectrum. So oftentimes it's good enough. It gives me the information I need. You want to know what's the frequency content of a signal, you throw it in, you look at FFT, you got these all these individual spiky signals, but you can look at that and say, I can see where there's frequency content. I got the information I need. I don't need exact values. It's all right. So sometimes that sample version is good enough. All we got to do is be careful about some rules so that this answers we get with these discrete samples do actually end up being samples of the DFT spectrum. Because there's a lot of cases where, if I'm not careful, they won't be. Why do I even bother? Well, because the DFT is great for computers. It's a sum. And it's a sum that a couple of clever guys won the Nobel Prize figuring out how to make it really efficient on computers. And it makes lots of interesting processing possible and fast. So again, the DFT, continuous spectrum, is the correct spectrum for our discrete time signals. We're looking at a discrete version of that on a good day. Both we assume are periodically repeating, just the DFT happens to be samples of it. And the particular samples I get back have to cover from 0 to 1. But that's all the information I need because everything else is just a copy. Okay. With one really big caveat. So I have sampled signals in the time domain. So we know, therefore, its spectrum must have what characteristics? Sample over here, what's happening in the transform domain? Periodic. Got to be periodic. Okay, no problem. The DTFT says we got periodic. We got it covered. We just, we know that this is repeating on. But now I'm taking that and sampling it, taking samples of it. Now I got samples over here. What does that mean is really going on back here in the time domain? Same thing. If I had sampled here, gave me periodic here, I got sampled here, I got sampled, but I also get periodic. So the DFT is the correct, the true, the right spectrum, not for my original signal, but for a signal that looks like a repeating copies of that original signal. What we call the periodic extension of the original signal. So if I had 8 samples here, took their DFT, looked at the sample values of that spectrum, those sample values represent the correct spectrum for not that signal, but that signal repeated over and over and over again. And I can't undo that. That's because it's a sampled spectrum, that's what it represents. Now, I can ignore that in some cases, but in other cases, in some of the applications and properties I want to use the transform for, I can't ignore this. I have to live with this. I have to work around this. That's what makes DFT signal processing a little more challenging. Anybody see where that comes from? Yeah.
So the signal that you're starting with is finite?
Yeah. Well, at least I'm using a finite number of samples of it.
I see, yeah. So
because I'm going to take those and plug them in the formula and get some new samples, the same number of samples.
okay. And because it is finite, can there still be errors with aliasing?
Because it's finite, can there be aliasing? Hold that thought till Wednesday. Not if it's truly a finite-like signal, but if, for example, it represented part of a periodic signal that had too high of a frequency, I could have aliasing. And what we'll see is that it could also, this periodic extension thing could also create aliasing with itself. That's kind of hard to grasp. We'll look at the pictures on Wednesday, though. So again, because I have periodic here, I get repeating here. As soon as I sampled this, though, I have the correct spectrum, but it's the spectrum of a periodically repeating version of that signal. Yeah. Where does that matter? Well, again, that tells me what I'm looking at when I'm looking at those sample values in the frequency domain. Those are one period of the repeating spectrum for the periodically extended version of the time signal. And why I do it is because, well, it's efficient for computers to find it. It's a summation, not an integral. So I like it. And when I take the inverse transform, I get a finite number of samples, but they represent one period of this periodically extended signal that spectrum was back there in the frequency domain. Right about now, it should be starting to sound like he's splitting hairs. What's the deal? Who cares? Doesn't sound too scary to me. Well, if you take a time signal, a finite length signal, take its DFT, get its sample values, take its inverse transform, and look at what you got, you get the right answer if the following is true. If you started out with m samples, well, that's what you get back out. First of all, we'll just plain ignore that it's a periodically extended signal, and sometimes I can get away with that. If your original signal back here truly was a finite length signal, and the number of samples you included did include every non-zero sample of that signal. So I got the whole signal and transformed it, and I inverse transform it to get back what I was supposed to get. I can use that signal, I can do what I want, it's all good. So as long as I got all of the non-zero samples included in the ones that I transform, then I inverse transform them and I get back the right answer. Or, it turns out, if m, the number of samples I'm transforming, is exactly one period or exactly an integer number of periods of a periodic signal, and I take its transform and I look at its spectrum, that spectrum is going to look good. It's going to look like what I would expect, as long as the number of samples I included was the exact number of periods. If I violate either of those two, then the spectrum I get is bogus. You can get the wrong answer if, for example, the number of samples you took and transformed and looked at a spectrum wasn't all of them. If I left out a couple, then I inverse transform. I'm basically looking at the spectrum of a periodically repeating version of this subset. Right? That's what I'm looking at the spectrum of. That's where I can get some aliasing. And the other place that it matters is when we apply certain properties of the DFT, and unfortunately it's the ones that are most important to us, the ones that are most interesting to us. Time shifting, modulation, and convolution, the ones we want to use for signal processing. Because when we do it with DFT processing, when we perform convolution in the frequency domain by frequency domain multiplication, or we apply time shifts in the frequency by operating on the DFT transform, we're not operating on the original signal, but we're operating on its periodic extension. It's a Fourier version. And so things like shifts become not linear, but circular. What does that mean? Well, here's a finite length sequence. We'll assume all the other values are zero before and after this bunch. And I want to shift this by 3 places. Okay, well, Fourier transform properties say if I want to do time shifts, I can take its transform, I can multiply it by some e to the j something or other, and inverse transform it. If I did that, what I would get is as if I took this periodically extended version, sorry about that, let's try that again, and shifted it, and kept the same number of samples. I get a circular shift, right? These ones here fell off the end, came around to the front. End around carries, arithmetic shifts, what do they call it? Arithmetic rotations, not logical rotations. Okay? That's what happens when we do frequency domain operations for time shifts using DFT transforms. When we get linear shifts, we get circular shifts. Same way for time advancing. It's not that we're advancing this one by 3, we're advancing this one by 3 and keeping the same number of samples and getting a circularly shifted waveform. Now, we don't often do time shifts in the frequency domain. What we do is convolution, which is flipping and shifting, right? So if I want to convolve two signals using transforms, I'll take the DFT of h of n, take the DFT of x of n, multiply those DFTs, and then take the inverse transform. If I do that, I want to be taking this x of n and taking my h of n, flipping it and shifting it past x of n, and each stage, each step, multiplying them, adding them up. Next stage, shift a little more, multiply, add. The flip and shift method. No, I want to do this, but I'm doing it to this. I want to flip and shift these two sequences past the other, but when I do it with DFT transforms, it's as if I'm doing it on the periodically repeating versions. So I get an answer that's not a linear convolution, but what we call circular convolution, involving the periodic extensions of those signals. Now, typically, at that point, we would throw up our hands and say, okay, well, this DFT is not good for anything, because I really wanted it to do convolution. I wanted to make that easy and fast on a computer, but I got this weird circular thing happening that's going to give me the wrong results. Was it really different? Yes, it's really different. And there was a tip-off that there's a problem. If x of n, let's say, has 10 samples, and h of n has 10 samples, if I transform each of them, each of their transform has 10 samples. Multiply them together, a transform of x times a transform of h, still got 10 samples. Inverse transform them, I got 10 samples. How many samples should I have if I convolve two 10-length sequences? Remember the formula? Convolution results. How long is the answer? I heard the sum minus 1. So if I convolve two 10-length sequences, I get 10 plus 10 minus 1. I need 19 samples to hold the true convolution result. If I do it with transforms, I only got 10. So right off the bat, I know I'm in trouble. I'm not getting the right number of sample value answers. I should get the length of the x added to the length of the h minus 1. But I get just the length, whichever one's longer. Well, and now they have to be the same length to multiply them. So there's appear to be some problems in using the DFT for convolution. And here's what the difference in results would look like. I took the same sequence and did a linear convolution of it with itself. I get these red sample values. If I do circular convolution with DFTs, I get the black samples. Notice kind of in the middle they're sort of okay, but because of the end around carry stuff going on, the circular shifts and convolutions, these outer samples are completely wrong. So very different result using doing convolution with discrete Fourier transforms, unless I'm smart about it. How do we be smart about this? Well, we got this, I want this. What do you think? How could we change this so that it looks like this? So when I slide these periodic copies of each other past each other, it's as if I did these unique ones sliding past each other. What do I want to do? Well, first I know I need more samples, because I need to get the right length. What else would I want to do here? Increase the space between them. You'd like to push these guys and you'd like to spread them out. Now, when they start doing that circular convolution thing, it doesn't matter. These don't overlap anymore. That's exactly what we do. We call that zero padding. We add a bunch of zeros to x, and we add a bunch of zeros to h, take the transforms of those bigger functions, multiply them inverse transform, and voila, we have linear convolution. And so whenever we do processing with DFT transforms, convolution processing, we're always zero padding. How long? Well, let's say each of these had a length of 10. I would add enough zeros so that this was, each one was 10 plus 10 minus 1, 19. I add 9 zeros to x, I'd add 9 zeros to h. Take the transforms of the 19 length sequences, multiply those, inverse transform, and have 19 linear convolution answers. That's how we do it with DFTs. So, exactly, here's, turns out with these ones, we had 7 samples, 7 non-zeros, 6, yeah, 7. So, here we actually did some extra. We zero pad out enough so that this length and this length minus 1, take their transforms, multiply the transforms, inverse transform that, and we get a linear convolution result. And if you do too many, no problem, you're just going to get the answer zeros. So as long as you zero pad enough to get a valid convolution length, you can get linear convolution instead of circular convolution by taking the transforms, multiplying the transforms, and inverse transforming. That's how we do DFT signal processing. So, so zero padding is a common thing we use to extend sequences to prevent circular convolution. We'll actually often use it. We'll make sequences longer so that the DFT computation runs faster. Now that seems like it's an oxymoron. I'm going to add more samples to this function so that the transform is faster. That shouldn't be, but it is a consequence of the algorithm that's used for fast Fourier transform computation. The other thing that it can help me do is if I add more samples, I get my frequency spacing. I have more samples dividing up the same range of frequencies, I get better resolution. So that's good for that. How does this wheel room work? How do I make a sequence longer and make the computation faster? Well, anybody know how the FFT works? Anybody ever looked into that? Well, FFT is a very clever algorithm that basically, it does a DFT computation, but it does it very efficiently. And how it does that is it keeps taking your sample values and cutting them in half, cutting the number of them in half. So if I have 16 samples, I'll make two sets of 8, and then 4 sets of 4, and then 8 sets of 2. And when I get it to 2, if you plug in in the formula, a DFT of 2 samples is the sum of the difference. That's whether the formula works out. That's easy. The trick is how I do those 8 sums and differences. The trick is how I put them back together to make the transform. That a little more complicated. But if you actually wrote out the terms of the transform, you would see a couple things happening. First of all, some of these exponentials keep happening over and over again. And so if you're smart, you don't recompute these every time you need them. You compute them once and put them away. So I can save some computation that way. The other trick is this. It's called a butterfly diagram. That each of these arrows represents a multiply, and each of these dots is a sum. This is how an FFT computation is done. That tear everything down into pairs and then put it back together. Here's how it puts it back together. Where these multiplication factors are those exponential terms that are computed once and put in here. They may be complex, but they're still easy to compute. And all the computer needs is this clever algorithm for how to put the pieces back together. Notice some of them we multiply by -1s, Some of them we multiply by exponential factors, but it's just the right cross combinations of sums and differences to create the transform values. And this is super efficient. Instead of the number of computations for convolving two numbers being like m squared, it's like m log base 2 of m. It's a much more efficient computation just by that clever stuff. So sometimes it pays us. What makes this efficient is if I can keep breaking things down in half and half and half and half and half with nothing left over. That means FFTs are blindingly fast if my number of samples is a power of 2. 2, 4, 8, 16, 32, 64, 128. So sometimes if I have like 60 samples, I'll pad out to 64 because it's going to run faster. If I have 100, I'll go out to 128 because it's going to run a whole lot faster. So we often use zero padding because it doesn't hurt anything and it can make the computation faster. Okay. When I add zeros in the time domain, what's that doing to the spectrum? Well, here's an example. Here I took a length 8 samples of a finite length sequence, took its DFT, and I got 1, 2, 3, 4, 5, 6, 7, 8 samples back, frequency samples, and they're plotted here. If I took that same number of, the same 8 samples, added 24 zeros to the end, and took the DFT of that, I get 24 samples, which are the black ones plotted, and the blue is the actual DTFT. So if I started off with a finite length sequence, and I had all the sample values, adding a bunch of zeros, all it did was give me a better spectrum. Notice my black ones exactly overlap the red dots, so they appear, and they actually do follow the DTFT spectrum for places in between. I get an interpolated spectrum. That's good. And that worked because those zeros that I added to my finite length sequence were actually correct values for that sequence. They were true values, right? So if I add true sample values, I get a better true spectrum. So if I started off with all the non-zero samples and got the red answers, if I added then a bunch of these guys, I got a better spectrum because these values are supposed to be 0. So I was actually adding information, true information, real information. So I got a better spectrum. If I did this, if I started off with not the whole thing, and then 0 padded that, this is the sequence that I'm looking at, the spectrum of, actually the periodically repeating version of that. I'm still missing this information. I didn't add any real information. Well, I guess I kind of did that here, but I didn't add true information here. So the difference between the spectrum that I got from these samples and the one that I got from these both are wrong. This one is prettier, but it's an interpolated version of the wrong spectrum. So we didn't add true sample values, so we're not going to get a better true spectrum. We'll just get an interpolated bad spectrum. And that's the first law of economics. You can't get something for nothing. There is no free lunch. You want a better spectrum, you got to put real data in there. Okay. So that's a lot to bite off. We're going to pause there. But to bring it all together, again, the DFT, Discrete Fourier Transform, is a sampled version of the DTFT, the real spectrum. It's actually the spectrum for a periodically repeating version of the finite length samples that we're transforming. And because of that, I have to take that into account when I do things like time shifts and convolutions by acting on the frequency domain version. But we can, with 0 padding, make that okay, as long as we include all the true sample information. And adding zeros is correct information. Then we can do all the signal processing we want with DFTs. And what makes them attractive is there's sums. There's things that computers can compute for us really quickly especially with the FFT algorithm that makes it artificial. Okay, Wednesday we'll look at what happens if you work with periodic signals. Weird things happen then if you're not careful. We'll talk about that then. And again, Friday we'll wrap things up, look at some applications, and talk about your midterms and the final exam. See you then.
I was wondering if you happen to know